Okay, so for those of you who might be confused, I'm not Jan. Okay, so the talk has indeed been swapped. Okay, so I hope you're not disappointed that you're going to hear about computational hardness instead of, I don't know actually what Jan will talk about. Anyway, so this is a work with a number of collaborators, amongst one, Lisha, who is sitting over here, and then some of my colleagues from NYU, and some of the former students that I actually managed to take from Barcelona to come to study with me. So keep it. I mean, these are very nice, very strong people. So keep them in mind for if you have to hire or if you have to take postdocs. Okay. So I'll start with the deep learning. No, I didn't start with it. Okay, so this is the starting. So I'll start with the deep learning slide just to set things on tone, but probably because in this workshop, this slide is not that necessary. But this is just to set the context, right? That we are in this period where we have all these, like nice success stories that typically at the beginning they only concern image classification. But as you can see now, the success stories get larger and larger, right? So now we are able to do completely crazy things with images, like for example transfer style. We are also able to solve many robotic tasks that rely a lot strongly on vision. Translation is also one aspect, and many manipulation on images and even like text and speech is something that is achieved by this family of techniques, right? And so I think it's safe to say that despite all the things that we don't know, there's something here, right? There's a proven ability to solve things in such a way that either we thought that they were not possible to be solved before, or that we had no clue how to solve them before, right? And so one way where we can start to advance our knowledge or to try to figure out why this is happening is to try to find some common denominator, right? So what do these tasks have in common such that like a relatively small class of techniques are able to do so well? Okay, and so as some Xavier discussed already this morning, we have here where we are facing with images, text, and speech. We have this very nice regular sampling structure, right? They all can be thought as images or like signals over a grid that lives in a low-dimensional space. So and I would say, actually, as also Arthur that is over there likes to say, another common denominator of success is the fact that we have this convolutional word, right? The convolutional is the most important word in the convolutional neural network, I think. And so what is this model capturing? And how can we maybe formalize why this convolutional architecture is so efficient? And maybe if we understand why, what is this inductive bias, maybe we can also use it, generalize it, to in more different problems where we are not dealing with images anymore, but as I will show later, problems in other domains, for example, in theoretical computer science or in combinatorics. Okay, so this is what the talk is going to be about. I'm going to try to talk to you about what I like to call geometric stability, and we are going to maybe try to understand what it means in an Euclidean domain. And then we are going to try to see how this notion can be extended in more general domains. And we are going to then try to leverage what we learned in problems that involve like graphs, and most of them are even inverse problems on graphs. Okay. So, and actually it's good that Stefan gave the talk yesterday, because then I don't have to, like give so much context, because really the setup of geometric stability starts with maybe trying to understand and set up the problem when we have to do solve a complicated task with images. For example, you want to do object classification, or you want to do object localization, right? You want to find object in the scene. So here we think about the data points, right? Not just points in high-dimensional space. It's true, they are points in high-dimensional space, but you have much more functional structure, right? You know that these points are actually functions. Okay, and there are functions defined on a very regular domain. Okay, and so any computer vision task can be thought as like a very complicated high-dimensional interpolation problem, right? Where we have to, there's an unknown function that maps images to labels, and we observe this function over a data set, right? We have just basically we know a function over a finite discrete set of points. We need to figure out what is the value of this function outside this set. Okay, this is a standard interpolation problem, except that it's not so standard because here the domain is huge, right? And so this again, we already had examples during the workshop. This is referred in statistics as the course of dimensionality, so you need assumptions, right? You need to have some prior in order to be, to have any hope of having this problem well defined. So when we are dealing with images, what are the reasonable priors, assumptions on this function that we need to estimate? So this is where a class of transformations that we can leverage the fact that points in this high-dimensional problem are images, are functions, right? And so in functions, we can do operations that you cannot do in a general vector space, which are, for example, taking a function and applying a change of variables, right? So you can think about this as you have an image, and if you want to add noise to the image, you typically add noise into the pixel values, right? You change the RGB colors. So here we are going to be adding noise to the pixel locations, right? You are going to change the locations of the pixels. So, and why is this a good model? Why is this a good idea? Well, because this is a kind of noise that allows you to do these kind of transformations, right? You can move, through different, paintings and different things. And as you can see a bit more technically, what this allows us to do is model many things that seem quite relevant when it comes to computer vision, right? We can model changing a point of view on an object. We can model different speakers, changing different tone or different pitch, etc., etc., etc. And so because we are adding noise, we have to quantify how much noise we are adding, right? But this kind of geometric noise, what is the amount of noise that we add? So of course this is is an arbitrary choice, but another like one measure that again is motivated by applications is to penalize by something that depends not so much on how much we move the pixel locations, but how much do we stretch things, right? You agree with me that if I take an image and I completely translate it in a rigid way, well, you would agree with me that the value of the function that I need to estimate is not going to change, right? So the more I stretch things, the more I can kind of destroy the contents of the image. Okay? So, so just for a little bit more formal, what we kind of postulate, right? We can even put this as a prior, is that many of the functions that we need to estimate are kind of continuous with respect to this noise that we add, right? They are kind of stable, so if we add a little bit of noise in that kind of noise, the function is not going to change too much, right? And so this is, for example, if we want to solve a classification problem. If we want to solve, let's say, a localization problem, right? Let's say that you want to find where the object is, right? So if you move the input, the output is also going to move, right? So that's what in some contexts is called equivariance. And so this in particular implies, translation invariance and equivariance when we, particularize these deformations to being rigid transformations. Okay, and so the point is that, whereas typical notions of translation invariance have been also used and popularized in computer vision, they typically involve a very low dimensional object, right? It's just the group of rigid transformations in a low dimensional space is not a very large object, right? Whereas the space of deformations is much large. And so this is something that we hope is going to help us, is going to give us a bit more leverage, okay? It's going to give us a bit better sample complexity when we learn. But of course, the question is, well, this is a prior, this is all very good, but how can you exploit it? What is the right tool to make use, to exploit this prior information? So I guess that everyone knows the answer, right? The answer is that, well, that seems to be a good match here, right? There seems to be a model that kind of plays well with this prior. And so, again, this is a slide that I could have skipped because this is, well, probably everyone is familiar at this point on what is a convolutional neural network, but it's just a cascade of very kind of innocent-looking operations that is just a filter bank that I concatenate as many times as I want by interleaving a point-wise nonlinearity. Okay, and so I can just keep doing that, but I can also reduce the resolution of the domain by applying some kind of downsampling or pooling or whatever. Okay. So why is this model geometrically stable? So why is this playing well with this prior that I described before? So if you think about, if you look at what would the deformation look like, right? This is of course a deformation that is going to stretch things around, right? But what a ConvNet is doing in this previous slide, okay, is just doing transformations that are localized, right? Okay, so it's just looking at filters that are localized in space. So if I look at this image in a very small neighborhood, right, and I apply a deformation of the whole image, if I look at the image only in a local neighborhood, the deformation looks like a translation, right? I mean, if I have a warping, if I localize it enough, it looks like a translation. Okay, this is true if the stretching is not very small. If the stretching is small. Okay, so as you know, if I translate an input, right, and I convolve it with a filter, the translation and convolution commute, right? So locally, I have this kind of nice commutation property, and here I'm really exploiting the fact that the kernels are localized in space. And when I take this property of like nice commutation and I cascade a nonlinearity that is pointwise, well, you agree with me that if I apply an operation that acts independently at every location, right? If I do a change of variables that I move things around, things commute well, right? There's no commutation error that is introduced by applying this nonlinearity. So the whole operation, the whole scheme of stacking layers that involve convolution and Poisson nonlinearities is basically defining as an architecture that commutes well with this class of deformations. And then I can basically kill this variability by applying a pooling, right? Like a downsampling operation that kind of gives me this local invariance. Of course, this is a very it's much more complicated than that. I mean, it turns out that Stefan, did like this very seminal work where he actually, it was actually proven that if you fix these filters to be actual wavelets, you can actually prove this thing, right? I mean, you can replace these approximations by actual theorems, and there has been some work that tries to generalize this stability to more general settings, right? Just replacing the wavelets with more general representations. And of course, this is also like a disclaimer. Here, this prior of geometric stability is only one half of the success story, right? I mean, if you have a representation that maps everything to zero, right, all these theorems hold, but I mean, the second part of the, why deep learning works is like the bit more mysterious part is, well, how can you get stability while being able to discriminate and, being able to express like a large class of functions, right? And so this is for another day, for another talk. Okay, so this is good, this is all good, but what we are interested now is, okay, how can we now think about this notion of geometric stability in problems that, for example, involve, as Xavier and Federico were talking about, let's say a citation network, or you have a network of people and you want to solve like a community detection problem. Or, as Kyle was mentioning yesterday, we are in this LHC, right? And we measure these, detection, like these particles that clash in the colorimeter, and we want to be able to basically discriminate between two different theories. Or, as Alan also was telling yesterday, right? We have, these molecules, and we want to be able to solve, like, to learn things, and we know that, perhaps we're going to exploit the fact that these things are also geometric objects, right? And so maybe if there's a notion of like geometric stability, how can we leverage it again in our models? And I believe that Michael is going to talk a lot about this setting where we are going to also leverage, and actually Michael and Leo discussed about also applications where we have to represent surfaces. So okay, maybe we can just take our functions that were nice functions living in a regular like functions of L2 or regular domain, and now we can just replace this domain by a irregular domain, right? The graph. And so like a graph here means a very general data representation that models a domain where functions live, right? And so here we are using a graph because this is an object that can represent metric, right? I mean, the distances between nodes encode like a metric structure that can be more general than the metric structure that we have in images. And so in some applications, even we are going to even identify the graph with the input, right? So not just the goal is not just to classify or represent functions in a domain. We can also even think about the problem of learning, like learning domains itself, right? And so we are going to mostly talk about weighted, undirected, and maybe weighted graphs. Okay, so these are represented again with a symmetric matrix. And so first step is, I would say like the simpler one, is that let's assume first that the graph admits like it can be represented, can be embedded in a low-dimensional Euclidean space, right? This, like, for example, if you think about the graph that would correspond to an image, right? The grid can be embedded in a two-dimensional space, right? So this is a class of problems, right, where already are pretty interesting in applications, right? In that case, I can represent my similarity as like a positive definite kernel over some coordinates that live in a low-dimensional space, right? So in that case, how can we take our notion of stability to deformations and apply it directly in this setting? So we can rely on the fact that there's this Euclidean embedding, right? That we can look at the graph as points in Euclidean space. And so since we know how to deform in Euclidean domain, we can just completely transfer deformations from the Euclidean domain, right, from the ambient space basically to the graph space, right? So this, in a sense, we are using an extrinsic notion of deformation. Okay, this is like this idea that for some reason the graph, like the translucid things that don't show in my slides, but you have to imagine that here there will be like a ghost graph that kind of deforms a little bit, right? And so this is a prior that maybe we can postulate, right? That if my goal is, let's say, to solve problems that come from maybe a lot of physical sciences, right? If I have some measurements that, correspond to these point sets, if I deform a little bit my input, you might imagine that, the output of whatever I need to predict is going to be close if these two graphs are close in some deformation measure, right? And again, this is another thing that you could motivate when you have to deal with surfaces, for example. So this is all good, but of course it relies very heavily on the fact that I can think about my graph as basically a planar graph, or something that lives in a low-dimensional space. So what about something that is a bit more intrinsic? So one possible one possible route, and this is something that we are exploring with colleagues from UPenn, Alejandro Ribeiro and his student Fernando Gama, we can think about the deformation, right, as doing a kind of a change of metric in our domain, right? If I look at my, I have two functions in my original Euclidean domain, and let's consider that I do this change of variables, this deformation, and I look I can interpret the action of this deformorphism as essentially changing the dot product, right? So now I can think about my deformed images as defining an Euclidean space that has basically changed the metric, right? I can, by just applying the change of variables, I have this object here that kind of distorts the metric, right? And so in that case, if you look at this quantity, right, this quantity is close to 1, right? If our notion of elasticity was small, right? So basically, if the amount of deformation in the previous definition is small, then it means that this metric is basically not far from the Euclidean metric, right? And we get something that also makes sense, because if we have, let's say, a change of variables that is an isometry, we might ask that maybe if we don't change the metric, maybe the representation should not see it, right? And so this way of looking at deformations in terms of changes of metric, maybe we can use it as a tool to generalize it to more general domains, right? To metric associated with an arbitrary graph. So the question is, how can we take an arbitrary graph and associate it a metric that can allow us to do something similar? So one possibility, not only, of course, by all means not the only one, is to think about the metric that is given by shortest paths, right? If you take a graph, you can define a distance, like a metric, that is basically obtained by defining the distance between any pair of nodes as being basically the shortest path between the two, right? And you can verify that this is actually a metric, satisfies the triangle inequality. And so once you have this object, it turns out that there's a very, very rich and profound body of literature that is concerned with basically comparing metric spaces, right? You can now define a distance between metric spaces, right? And one possibility is something that is called the Gromov-Hausdorff distance, that has this complicated a priori expression, and I will explain in a minute how can you think of it in a more simple terms. And this is actually an object that has been very popularized in surfaces and analysis of surfaces by Guillermo Shapiro and his collaborator Memoli, and also by Michael and Alex and Ron Kimmel already some years ago. Okay? So of course this is a very ugly looking structure. It involves, so when you particularize it to a finite metric space, like a metric space that has like a finite number of vertices, you can think about it as solving a kind of a matching problem, right? You say, for all possible ways I can map points in one graph to points in another graph, okay? I will look at how the shortest path distances are going to be distorted, right? And so if I'm able to connect to, basically if I'm able to make this thing 0, but essentially what you have shown is that the two graphs are isometric, right? Isomorphic. Okay, so this is all good, and so the one thing that we can postulate, right, is that if the two graphs, basically that this might be a potentially good prior to do inference and to solve problems that involves graphs. In the following sense, right, that maybe what I can postulate is the function that I want to estimate as before. If I try to compute this function on two graphs that are close in this metric sense, maybe the function that I need to estimate is also going to be continuous with respect to this distance, right? And I will try to motivate later why, for example, problems that involve, for example, community detection, or if you want to do planning on a graph, you want to solve planning problems, right? Maybe the planning is a tool, is an inference problem that is continuous or is stable with respect to these kind of metric deformations. Okay, so how can we leverage, again, this kind of stability on graphs? Okay, before, like like some minutes ago, we had the same question on images, right? So now how can we do the same thing on graphs? So we had also like the taste this morning, right? Is that what are the equivalent of the CompNet on a graph? So for this, maybe we can use this as a kind of a motivation, right? So if we look at what happened in the Euclidean domain, right? We kind of I kind of gave you a slide that tried to convince you that one possible way to get stability is to operate, to work with a family of localized multiscale filters, right? And you can think about these filters as a kind of a differential operator, right? That is discretized in this domain. Okay, so here again, I'm sorry for the fact that you don't see the translated things, but the idea is that if I have an Euclidean domain, I can define a bunch of partial derivatives, right? These are just little filters that look at the derivative of a function over different directions, right? And so these are operators, differential operators, that are stable to deformations, right? If I do a partial derivative, because it's a local and it's a convolution operator, it has the nice commutation property with respect to the deformation. And in fact, if you wanted, right, you could write the CompNet in this way, right? You could say, well, a CompNet now is just going to be a linear combination of these differential operators, right? And the only thing that the CompNet is learning is the coefficients of this. If you want like a polynomial, right, is that you have a family of generators, and then what you learn is basically the right differential operator that can be written as a linear combination of these kind of atomic stable generators. Okay, and then I use the pointwise nonlinearities because these are kind of harmless when it comes to deformations, and then I continue again and again. So what about general graphs? So in general graphs, it turns out that we can define almost as a very simple, almost by definition, a linear operator that is just doing a diffusion, right? That basically is given by its own adjacency, right? If you take a signal on a graph and you want to blur it, right, what do? You multiply it with the adjacency matrix that is going to basically blur, is going to construct linear combinations by its neighbors, okay? And almost by definition, this operator is basically up to isometry is stable, right? Because it's almost the definition, right? By definition, if the distance between two graphs is small, it means that basically I can, by finding the right permutation, the right isometry, the differences in the weights is going to be small, okay? But this is not very interesting because it's just blurry, right? It's just a low pass. But it turns out that again, if you have a low pass, you have everything, right? Because if you can do like an all pass filter, right? If you have the identity or something that looks like the identity, you can construct a high pass by, and in terms of the all pass and a low, you can construct a high pass filter by, taking an all pass filter and removing its low frequencies, right? And that's the idea is that, if you have a building block that is stable and you use something that is also stable, then the resulting operator is also stable, okay? So what we ended up here, essentially, is the same story as in a CompNet, right? The same way that the CompNet it can be written as a linear combination of basically stable differential operators, we can do the same thing on a graph, right? Except that, of course, now the family of operators is a bit more humble, right? The only thing we know how to do is basically to diffuse, and maybe we can compute the all-pass filter, okay? And we do the same thing as before. We just learn linear coefficients here. We apply a pointwise nonlinearity, and we iterate, right? And this is actually a model that was introduced, is already like old for. As someone was telling yesterday or 2 days ago that all was like 1 year in machine learning, right? So this is like it's much more than all, right? It's like Yeah, prehistoric. Okay. So, but in a sense, it's very interesting that now it kind of resurfaces because maybe it was not introduced using the same spirit, in the context of building like something that is close to a CNN. But it turns out that so the initial version was more inspired as a kind of a tool to approximate message passing algorithms. By basically using a recurrent, basically all the layers at the weights at every layer were kind of tied together. And so many, like some of the researchers, in particular Sanya and Arthur that are here, and David Duvenon from Toronto, and Lee again from Toronto, they kind of realized that, the same way that, if you look at a CompNet, no one trains a CompNet with the weights that are tied, right? Everyone just, the simplest thing is just to say, well, I just, I decide a priori how many layers I want. I can basically learn a number of I can learn different weights for every layer, and I just train everything end to end. So this is actually what I call by modernization, because in a sense it makes things work very, very well in practice, right? And so again, it's something that also like Xavier described today, so I'm not going to spend a lot of time, right? Is that this thing you can modify it and extend it in a number of different ways. So again, as I said before, because the Laplacian is just, because here we are learning linear combinations of basically a low pass and an all pass, right? You can reparameterize this equation, and if you want, you can make the Laplacian appear, right? It's just a reparameterization of this family of generators, right? And so if you want to write your GNN in terms of the Laplacian, you can do it, right? And if you take powers of the Laplacian, then what you end up with, right, is basically every layer of this network is just learning a linear operator that can be written as a polynomial of the Laplacian. And so what are the class of operators that this model spans is basically all the operators that commute with the Laplacian, right? Because a polynomial commutes with the Laplacian, right? And so in other words, what you are learning is basically an operator that can be written diagonally in the Laplacian eigenfunctions, right? So that was the initial story. As Xavier presented this morning, this thing is is interesting from a theoretical perspective, limited practical interest. And in particular, they had like some problems. Of course, there were some issues in terms of, it was defining an operation that was a bit too expensive in practical applications. And so luckily, Xavier and Michael and Pierre van der Geest kind of realized that there's a much more intelligent way to do it, is to use basically to work directly on the spatial domain by exploiting a polynomial of the Laplacian in terms of Chebyshevs. And also, of course, as Xavier presented, Thomas Keefe and Max Welling also have to be credited because they were basically the ones that showed that this thing really works, right? That can work in practice. Of course, you also show that it works, but they also show that it works, okay, in different domains. So, okay. So what are the extensions or limitations of this model, right? And some people might ask, okay, this is all very nice, but when you apply this to an image, do you get the CNN? Well, the answer is obviously no, because here our family of operators is just a Laplacian, right? Our only way to compute a high-pass filter is to do a Laplacian. And as you know, the Laplacian is an isotropic operator, right? It doesn't look, or it doesn't see orientations. In a sense, this is not the fault of the machine learning researcher, right? It's not that we didn't come up with a better operator, it's that it's like an intrinsic problem, right? On general graphs, there's no notion of orientation. But again, machine learning researchers are very stubborn and very, they really want to push things. So there are ways in which you can improve these things. And one that is in particular that makes sense is, and again, I think that someone asked this question today, is, well, maybe what you can do is kind of build upon this architecture and maybe, also work not just in the signals that are defined over the nodes of a graph, but also over the edges of a graph, right? And one possible way to do it is, so there's a lot of papers recently that kind of leverage on this idea, in particular papers from DeepMind and all, like people coming from DeepMind and coming from Google Brain, where they kind of combine, yes, Arthur? Really? Oh, wow. Okay, so you see, so these things is really even prehistoric. Okay, so yeah, so these things you can actually, extend it to, you can do many interesting things, right? And so, In particular, just let me mention, like very briefly, one particular thing that you can do to basically recover orientation is maybe when you have a little bit of structure. I said before that in general graphs there's no orientation, right? But what about if we have a graph that is kind of modeling a surface, right? That is representing, like a surface in 3D. So one way you can do it is to like basically to do like a piecewise linear approximation, like that is like with a mesh, right? With a triangulation. So in that case, it turns out that we can, compute. So basically, if you think about a Laplacian, the Laplacian, you build it by basically taking the gradient, okay, which is an operator that has orientation, and composing it with its adjoint, right, which is the divergence. So in a sense, what you would like to find is there like a square root of the Laplacian, right? Can I compute a square root of the Laplacian that kind of hopefully has a spectrum that is kind of meaningful, right, that recovers orientation. So it turns out that in the case of surfaces, the answer is yes, right? And there's actually an operator that comes from, I believe, quantum mechanics. Okay, so if there's people here in this room who are experts in quantum mechanics, please correct me if I say something wrong. But the idea is that this Dirac operator is an operator that kind of generalizes the gradient on a general surface, right? And the price to pay that is not small is that it's not just a complex operator, but it's actually an operator that is defined over quaternions, right? Which is a kind of a fancy version of a complex numbers. And so with this, what the nice thing is that we have this operator has nice properties. It's stable to deformations, and it's actually stable to discretization. So it converges to something, right, in the surface, in the manifold. And so we used it in a paper with my PhD student, Ilya, Daniele Panozzo, and Denis Zorin. These are colleagues from NYU. And so the sort of thing that we applied this model for is trying to predict complex nonlinear dynamics, right? So we basically take, pieces of body, right? So sorry about the thing. So we just take Faust and we extract some, body parts, and we just have a physical model that throws them into the floor. Right, and of course, because the body parts have this very complicated elasticity, we use a complicated physical model that is really, of course, nonlinear, and then we try to ask the network to predict, right, to try to predict these nonlinear dynamics using different versions of this GNN. Right, and what you get here is that, well, if you don't use, if you just, so this is the ground truth, if you don't use, if you try to predict every node of the mesh independently from each other, you fail miserably, right? I mean, you can see that this thing is not capturing anything. If you use something that would be maybe assimilated with the early version of the point net, right? That is something that we heard about yesterday, where you only combine either localized information or global information. So you don't use the geometry either. You get something that is surprisingly good. So it really tells us that, there's a lot of structural information that can be captured here. But if you look in detail, you see that there's a lot of things that they don't the physics are not well captured. Not surprisingly, because it doesn't use any kind of geometric information. And you have to look even more carefully, but you can see, if you believe me, that if you compare an operator that is isotropic with a Dirac, you can see that in places where you have like the anisotropy is important, you get like some improvements. And you can check more details in our paper if you want. And we have these nice videos, but we have also like a very basic stability theorem that essentially what it says is that the bottom line, I mean, you don't need to read the whole thing, but the bottom line is that same as before, right? If you can give me a family of operators that are stable to deformation, okay, then I'm allowed to use them within a GNN, with a network that consists in learning linear combinations of these things, nonlinearities, and cascading. Intuitively, you would say, well, if you only do manipulations of things that are stable, the overall thing is going to be stable, right? So that is just doing the legwork to make this thing work, and everything works well, except that in a sense, for these things to be meaningful, right? The problem, and maybe some people here more prone to numeric analysis will detect it, is that the Laplacian operator is not bounded, right? As you keep making the mesh larger and larger and larger, basically the spectral radius of the Laplacian diverges, right? And so how can you get something stable despite this fact? You need to assume that the signal is smooth, right? And so so this is something that we still need to assume here in this theorem, but I believe that this thing can be completely work on with something that we are currently thinking with my students, right? Just to extend this thing in a more general setup. Okay, how much time do I have left? 10 minutes. Okay, perfect. Okay, so now I want to maybe see how this thing can be used, and like this, to try to tell you how are we using this kind of machinery to problems where have essentially nothing to do with images, right? So, and I want to start with a problem that is again very kind of well known in people who work on networks, but also people who do more like statistics and theoretical computer science, that basically consists in the problem of inferring the communities between two graphs, right? Between a graph. So let's say that here, you know, again, you have these people from Los Angeles, people from New York, okay? And so, you know, depending on which city you are from, you have a probability to be connected with your friend or not, right? Depending on if the friend lives in Los Angeles or New York. So this looks like a, you know, of course, when I show you the graph like this, it's very easy to cut it, right? But what the model is basically saying is that, well, this would be the, you know, the output result. So if I hide you the labels, right? The only thing that you observe is the adjacency, but here I'm still giving you the labels because I'm arranging things in the right way. What you see is this, right? So you have basically this is your input, and you need to infer that here there's a clustering structure, okay? So this is, of course, an inverse problem, right? And so how is this approached? And so one way where it has been very successful in, I would say, in statistics and theoretical computer science is to try to think about this problem in a kind of simplified random graph family. Okay, and I think it was mentioned already today. One particular one is the stochastic block model. Okay, so the stochastic block model is just saying is like the simplest possible one, where I say, okay, I have just two parameters. What is the probability that I, in the case where I have two communities, what is the probability that I connect with two, well, I draw an edge between two nodes that are in different community, and this would be probability B, and what is the probability to connect with the nodes that are in the same community, A. And so, how hard is the problem? Depends again, as people who, as in many inverse problems, it depends on a signal to noise ratio, right? How much signal I see versus how much noise I have. So here, the signal to noise ratio is a function of how different are these probabilities, right? Versus what is the kind of the average degree. Okay, so how much, basically, how much connectivity I see. And so there are two major ways where you could think about this problem. One is to try to characterize the solutions as minimizing, optimizing certainly like a carefully chosen quadratic form, right? You could say maybe I can define like this energy that is maybe like the conductance, right? Something that that captures how separated is the graph. And then I can try to optimize over my labels this quadratic form. Of course, this, you can see here, it's an intractable problem, but there's ways where you can relax this thing and then use techniques from semi-definite relaxation on spectral methods. The other approach is to take more like a probabilistic, like a Bayesian approach, where, well, if I know how the data has been generated, I know the likelihood, right? So I can maybe just infer by basically maximizing the posterior likelihood, right? Maximizing the posterior. So it turns out that this is something that in general graphs it's intractable, but you can use like a method that is called belief propagation that basically is tractable, and in many cases leads to very successful estimations in this setup. And so there's a nice research that I'm not going to be describing here that kind of unified those approaches and is able to answer the questions very precisely. For example, what is the amount of signal to noise ratio above which I can make this problem feasible as I make the size of the network larger, right? And not only that, when can I solve this problem using a polynomial time algorithm, right? So this is what's called an information theoretical gap, and this is what is called like a computational gap, information theoretical threshold, and this is the computational threshold. So one question here is that, well, in this setup, like more like a sanity check, right, to analyze, how these networks can be good, is, well, to what extent you can, introduce learning into this picture, right? Can you learn these algorithms from data, and how well do they do relative to the best that you could possibly hope to do? So this is a joint work with Alicia Lee, who is sitting there at the room, and so what we ended up is that basically, well, we start with we can maybe take inspiration from how the spectral methods work, right? So in a spectral method, what it's going to do is that I take a linear operator on a graph, for example, the graph Laplacian, and what I will do is that I will basically take the Fiedler vector, which is the eigenvector that corresponds to the second smallest eigenvalue, and I take the sign. Okay, that is the case where I have two communities. And so by using tools from random matrix theory, you can prove that if the signal-to-noise ratio is sufficiently large, as the size of the graph increases, there's the spectral gap, right? There's basically the thing that corresponds to the ground truth separates from the bulk of the spectrum, so you can hope that this thing correlates well with the solution. But the point is that now we are going to basically try to do like a data-driven approach. Okay, so what we do is that we can look at this as an estimator, and what is the, when you need to extract eigenvalues, eigenvectors, typically what you can think about is doing power iterations, right? And power iterations is just an iterative algorithm, right? It's just basically applying an operator that is maybe properly rescaled and basically projecting it in some way, right? Either normalizing it or, doing something. So again, following the idea from Jan and Carol Gregor, like that they did the same thing for sparse coding, you could do the same thing. You could enroll this algorithm and just train end-to-end, right? And when you enroll this algorithm, what you get is of course, is a GNN, right? It's basically something, is an operator that of course, has to alternate between, optimizing an operator, except that here we don't know which operator, right? A priori, we have no idea what is the right operator of the graph that you need to iterate before you get the solution. So we could just consider a general GNN, and we just, you can show that this is a good choice of generators because it contains something that is called a Bethe-Hessian. I'm not going to explain what it is, but essentially you can think that if you are able to represent this operator, you are in good shape, right, for this model. And so we train everything with backprop, and what we get is something that, as a function of the signal-to-noise ratio, okay, in two different settings, what you see is that this model is actually basically reaching the best performance that you could actually hope for, right? And this is like more like a sanity check, right? So in this case, what the clustering power of our algorithm does, as well as essentially, this is the optimum algorithm that could work in this problem in this case. And so this is not good this is nice to like in this kind of a toy problem, right? The stochastic block model. And the nice thing also is that you can use it in real-world community detection, right? And so we used actually data from Juris Leskovec's lab, who I believe is here. Yeah. Okay. Good. So we took like a very, very nice. They have a very nice repository of large graphs that have annotated communities, and we kind of transform our setting so that we can apply the machinery. And what we see, not surprisingly, is that once you have a trainable model that has a lot of enough parameters, you can do well on the stochastic block model, but you can do well on a data-driven, like on a real-world data set, right? And so this is, I believe, a model that is called like, I don't know, I let you to talk because I don't know exactly what this model is doing, but in a sense it's like a baseline that uses like of course a smaller set of parameters. Okay, but this is just to show that these things can be used in practice. Okay, maybe I'm gonna skip this. Okay, so well, maybe 5 minutes. Yeah, perfect. So, but it turns out that if you go back to the how hard is this problem, when the number of communities is small, like in that case 2, there's no gap. Okay, it turns out that belief propagation, you can prove that it reaches basically the information theoretical threshold, right? So in a sense, there's no mystery on what is the best polynomial time algorithm that can solve this problem, right? But basically we have an algorithm, right, the belief propagation, that is essentially optimum in the class of polynomial time algorithms, right? And so what is belief propagation? Just a crash course in one slide, is an algorithm that is going to propagate messages through the graph. And the messages live in the edges of the graph, right? And again, this is again a question that was asked before, is that these messages that are functions on the edges, right, are kind of updated by exploiting the adjacency structure of the edges, right? So basically, and in particular, it takes into account what's something that is called the non-backtracking path, and this is actually very important in the stochastic block model. So the question is, well, how can we maybe use our GNN that is able to do exactly the same thing, right? So that to propagate information on the edges of the graph. So the GNN version, as actually Jan suggested, in passing is, of course, like it's a very natural thing to do, is to change the graph, right? You can take the original graph and define what's called a line graph, right? It's basically a graph that has, where now the nodes become the edges of before, right? And the edges of the new graph correspond to basically the adjacency of the previous edges, right? And And in a sense, it's just a way where you can now completely approximate message passing, like a belief propagation, as basically an instance of the GNN, right? And again, this is a model that is now we're in this period where every week there's a new GNN model, GNN paper, and there's like a very minor variations, like model exploration around these things. So there's these covariant computational networks from Condor that do something on the same vein, because of course, once I know how to do the line graph, of course, you could imagine doing the line of the line and the line of the line of the line, etc., 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 right? So you basically, you can create like a whole zoo of GNNs that, of course, every time become more and more large, but you can see where I'm going, right? So with that, you can now try to attack this question, that is the computational to statistical gap, right? So what happens if I now try to learn something in a case where no one knows how to do, right? So basically, and this is something that you can generate when the number of communities is like larger than 4. Okay, so this, you can think that is like a graph coloring problem, right? You have like 5 colors, and you know that you are not allowed to connect if you are in the same color as yourself, right? So you need to find a coloring of a graph, and depending on the average degree of the graph, it turns out that there's a gap. Okay, so you don't need to understand many things, but the point is that depending on the average degree, there's a regime where there is, if I could do maximum likelihood, I could find a configuration that correlates well with the solution. But if I run belief propagation, I fail completely. Right? There's no hope there. So you could imagine is that now we have put belief propagation as a point in our parameter space. Right? Now we are kind of learning models that contain belief propagation. So one natural question is, well, can you maybe find a point like that is not belief propagation that does well in this regime? So this is, of course, the research program, and so I don't have good positive answer for you today. But what I can tell is that already, what we get is that in finite sample regime, we are at least what we can say is that in this super hard regime, we are basically doing as well as VP. Okay, so. This is not, of course, it's not answering whether this gap exists or not, but it's just to tell you that we have this machinery that now we can use, basically maybe by making the graph larger or by changing the way these things are trained, that we can study these sort of questions. Okay, so I will just very briefly talk to you about a couple of other problems, and I will conclude. Is that another problem that we studied using this machinery is the quadratic assignment problem, and this is joint work with Soledad, Alex, who is now at NS with Francis Bach, and Afonso Mendeira, who is a colleague of mine. So what is the quadratic assignment problem? Is that you have basically factories, right? And the factories are, they have some cost of sharing things with each other, and you have some sites that also are separated by some distance, right? And what you find is you want to find an assignment between two graphs in a way that you want to minimize the distortion, right? In that case, you want to minimize the fact that, basically the mismatch between the metrics between the two graphs. So again, solving this problem is, of course, a very similar problem from the one I described before, like computing the Gromov-Hausdorff distance, and it's NP-hard. You can show that it contains the Treble-Simmons problem as a subcase, right? If you choose this to be a Hamiltonian cycle, this is a generalization of the traveling Simmons problem. And how do people try to solve this problem? They try to relax it. Okay, so rather than minimizing over the space of permutation matrices, you try to minimize over a nicer space, right? And so this is something that you can do with semi-definite programming. So how do we do it? We are not going to use this thing. We are just going to use our tool, right? Our GNN. And so the way we instantiate it in this case is using a Siamese architecture. Again, something that has been known and used for many years in machine learning by Jan and some of his students, where we take the two graphs, we embed them using a GNN, and now the idea is that in this embedding, we go from a quadratic assignment problem to a linear assignment problem, right? And the linear assignment problem is tractable. Okay, you can solve it, for example, using the Singhorn iterations. Okay, and so the way we train this model is again using this idea of planted solutions. So basically what you do is that you promise the model that there's a solution, right? And then you ask the model to find it. And so we do this by basically constructing a data set like this. And what we see, interestingly, is that in two, let's say, settings that are kind of still under experimentation, what we see is that, again, in terms of the signal-to-noise ratio, our model is able to basically do essentially as well as the best relaxation that is known. And in the case where we are using like a graph model that is much harder, we are significantly improving over like the known relaxation, like SDP or spectral relaxations. And we do that with a complexity that is remarkably smaller. So there are a lot of things that we don't understand of this thing. For example, what is distinct learning, why it works. So it's related, you can think that if you want to align two graphs, right, you need to find features that are kind of distinctive of every neighborhood, right? And so you could imagine, well, what if, the spectral information, right, basically the spectrum of the Laplacian can be something that is distinctive, but only when the spectrum is kind of simple, right? And this is something that is called corresponds to simple graphs. So one hypothesis is because now we are not just propagating one operator, we are propagating a family of operators, right? We have every layer, we have a different number of feature maps, right? So we are helping the model to align not just the spectrum of one operator, but because we have this ensemble, this is something that might be an hypothesis of why it works well. And we are also, it turns out that this problem has a lot of applications, shape correspondence, but also, if you want to align, like do translation of two languages, and you have no alignments, right? You can look at one language as one graph, another language as another graph, right? So the quadratic assignment problem can be thought as basically finding this correspondence. Okay, and this is, I promised, the last slide. So the last thing that I would like to talk to you, the thing that we are doing, is something that I think that I was introduced to this technique by Jan some years ago, and I found it quite fascinating, is that, okay, let's say that you have a unitary matrix, okay? For example, the unitary matrix that diagonalizes my Laplacian in a general graph. And as Xavier said, this is an expensive operation, right? This is super, I mean, I have to pay, if I want to use this at, at test time, I have to do this expensive matrix multiplication. And as we know from Vinograd, this complexity in general case is like quadratic, right? But we know that for some structured matrices, you can really, completely break this barrier by exploiting like some symmetries of the matrix, like some kind of algebraic structure of the matrix can yield to significant improvements. So what about the general case? So it turns out that, and again, we had yesterday, Miki was telling us about the sparse land and the sparse, how can we use sparsity as a prior. So you could think about the same thing as basically what is the equivalent of a sparse decomposition, but not just of a vector, but of a matrix. And I like, Arthur likes to call it like a logarithmic sparse coding, right? Because it's actually a nice way to say it is that, the equivalent of, a sparse vector, a sparse decomposition of a vector is the sum of things. So what would be the equivalent of a sparse decomposition of a matrix? It's a product of matrices that are kind of atoms, right? And so this looks like a logarithmic sparse coding indeed. And so this is the tools, the bricks that you use are very simple matrices that basically look at the plane, like a pair of coordinates, and just rotate it within this pair of coordinates, right? And it turns out that, of course, if you use a lot of these things, you can approximate any operator. But the goal of the game is whether you can find approximations that use a small number of terms, right? Again, going back to this notion of sparse approximation. So, of course, the bad news is that this thing is NP-complete. And it's, as opposed to the sparse coding, it's like completely non-commutative, right? You have, the algebraic structure here, right? Multiplying matrices is more complicated than adding vectors, right? And so it's a complicated manifold optimization problem. And so what we are trying to do here now is basically to use, again, a graph neural network to learn these factors, right? And so how can you do that? I mean, how can you set up this problem? And this is current work with my student, David. So we are, again, using a planted setup, okay? So we promise the model that there's, that there's a sparse factorization, and then we try to find it. And because we are training with basically these labels, we can just transform this in a completely supervised learning problem. Okay, and so we are using this, basically a graph neural network on the fully connected graph that is defined by the matrix, and we use basically a multi-set loss to account for partial permutation. So I don't have, of course, this is still very ongoing, so what our preliminary results seem to show is that already this thing is not doing something stupid, it's matching what you would do by basically using a greedy algorithm. But I hope, in the future, I'll let you know if it works. But this is like ongoing interesting things. So I will just gonna wrap up. So I hope that I try to present like some, like a story where we can use basically this notion of geometric stability to move from basically the, convolutional networks and their success in images to like another land of, like a land of problems where maybe you can leverage this stability to attack like a wider set of things, right? Of course, there are many things that we need to figure out before. What is the, is the graph of the right notion, or if there's some alternative? Is it actually possible to use these tools to study these computational to statistical gaps? And of course, as you can imagine, there's huge potential for applications, right? So biostatistics, physics, as Kyle was talking about yesterday, combinatorial optimization, many things. So yeah, so thank you very much, and I'm open for questions.